I'm going to quickly go over some points about torque and static equilibrium and mechanical advantage. Here we have a teeter-totter type thing, and on this side, close to the fulcrum or pivot point, here's the pivot point, there's a big heavy mass, and over here farther out is a smaller mass. And it so happens that these are the right size masses at the right distance from the pivot point to let this teeter-totter system be in static equilibrium, which means it's not moving, it's just sitting there balanced perfectly. Why is this? Well, it's not rotating because the sum of all the torques around the axis here are zero. And when we look at the rotational version of Newton's second law, this is Newton's second law, the rotational version, force becomes torque, mass becomes moment of inertia, acceleration is rotational. Solve for rotational acceleration, and we can see that if the sum of all torques on this teeter-totter is zero, then the rotational acceleration must be zero. If it's not accelerating angularly, then it's just going to stay put like it is. Okay, now why is the sum of all torque zero? We look at these masses. This is a heavy mass, so it's got a lot of gravitational force pushing down, whereas this one only has a little bit. So from that, it doesn't look like it's going to be in rotational equilibrium, but we have to consider the torque. Remember, the torque is the force, and we've drawn force vectors here, times the moment arm. And the moment arm is this distance from the axis of rotation to where the force is being applied. So the moment arm for this force 1 is pretty small. So the torque 1 equals a big force times a small moment arm, and over here we have a small force times a much larger moment arm. So the second torque can be equal to the first torque because even though the force applied on the teeter-totter is smaller, you have to multiply by the much bigger moment arm. So because these two torques around the axis of rotation are equal, they cancel each other out, and you get the sum of all torques equals zero. We have static equilibrium in terms of rotation, rotational static equilibrium. But what about translational static equilibrium? This teeter-totter board could not be rotating, but maybe the whole thing is just going upwards. Actually, from the force vectors we've drawn already, it looks like it's going downwards. But we've forgotten to draw an important force vector, which is this here. There's force from the fulcrum part on the teeter-totter board, and that force is equal to this force going down plus this force going down. So this total force pushing up is equal to the sum of the two forces pushing down, and therefore it's also in translational equilibrium. Okay, just for fun, let's pretend that this point over here at the end is the axis of rotation. If this thing is in static equilibrium, we should be able to calculate a sum of torques equals zero, assuming this is the axis of rotation. So if we're no longer considering this point the axis of rotation, this force here is providing a torque around this point, this axis of rotation over here. So what should be true is the torques around point A, let's call this point A, equals the torque applied by this force, let's call that, this is point B, we'll call this force FB. times the moment arm of FB, which is the distance of this force to what is our axis now at point A. So that's the distance R1. And then there's also another torque acting around the axis at point A, which is this F2 over here. And here's a funny convention. If a torque is acting clockwise, it is negative. So since this one is trying to rotate clockwise around point A, we have to call it negative. So we're going to subtract the torque, which is F2 times the moment arm, which now becomes the distance from F2 here all the way to point A, which is the distance R1 plus R2. And since we know this thing is in static equilibrium, the sum of all torques must be 0. So that means the magnitude of this torque is equal to the magnitude of this torque. A cool result of this is that one can use a kind of lever fulcrum system to use a little bit of force to lift very heavy objects. So this is a very heavy object with a lot of gravitational force. We don't want to strain our back to lift that. We can just push down with a little bit of force over here, and that little bit of force will provide a lot of torque because of this large moment arm. And if this amount of torque provided by this force with this moment arm is at all bigger than the torque provided by this force with this moment arm, then you start to have rotation and you lift this object up. So this is an example of mechanical advantage because you are getting out more force than you are putting in. Alright, that brings us to the really cool application here, which, okay, follow me. Use your imagination, stretch your imagination, and pretend that what we have here is a yardstick that's hanging halfway off of a table. So here's our table. This big thing with the lines in it is a yardstick. And what we've done is we put an 80 kilogram mass here and a 50 kilogram mass here. There's 20 centimeters between the masses and 20 centimeters from the 80 to the edge of the table here. And let's say we are given a 100 kilogram weight. And the question we are tasked with solving is how far from the edge can we put this 100 kilograms without having the ruler rotate and topple over and fall off the table. So our task would be put this 100 kilogram weight as far as possible from the table without making the ruler rotate around this axis and fall over. Boy, I'm thinking about this. This is a lot of mass. That would just snap the ruler. Let's turn these all to grams. Alright, I feel better about that. Alright, so let's think about what's going on right now before we put this 100 gram mass anywhere. It's just still in our hand. Okay, there is a gravitational force from this 80 gram weight, a gravitational force from the 50 gram weight. Those forces are providing torques clockwise around this axis of rotation. Why isn't this accelerating in the clockwise motion right now? Why isn't it accelerating clockwise? Because the table is pushing back up on the ruler here. There's a normal force, and that's providing a counterclockwise torque in the other direction. The torques cancel out, and you get the condition for static equilibrium that the sum of all torques around the axis of rotation is 0. Now, when we put the 100 gram weight on, we still want the sum of all torques around this axis to be 0. But what we also want is for the force that's applied by the table to the ruler over here, we want that to diminish as much as possible. We want it to actually diminish all the way to nothing. Because when the table doesn't have to push it all on the ruler, and it doesn't have to provide any counterclockwise torque, then that is the maximum distance that we can put the 100-gram weight over here. But anyway, long story short, if we've put the 100 grams as far as possible from the edge of the table, then the only 3 torques that will be acting are the torques from the 3 masses that are there. This one, and this one from the 100 grams. These 2 will be acting clockwise, and this one will be acting counterclockwise, because it'll be trying to rotate that way. So here's the part you've been waiting for and looking forward to, the actual equation we can use. We know that sum of all torques will be 0, that's the condition for static equilibrium. What are those 3 torques? The positive ones, those are the counterclockwise ones. There's only one of those. It's over here. So the force there is the 100 grams, which is 0.1 kilograms. It's not a force yet, that's the mass, but we can turn it into a force by multiplying by g, the acceleration of gravity. So that's a force, but a torque is a force multiplied by a distance. The distance is the moment arm, and here the moment arm is that variable we're solving for, x. So we've essentially got a torque, an F times R here for the counterclockwise torque. And now we have to do the clockwise acting torques. And because they're clockwise, the convention says we call them negative. So we have to subtract the torque from this 80 grams here. Alright, this is the force. The 80 grams became 0.08 kilograms. And we turned that mass into a force by multiplying by g. And to turn this force into a torque, we multiply by the moment arm 20 centimeters, which is 0.2 meters. Now for the last clockwise torque, we're going to subtract it because it's clockwise. There's the force applied by the 50-gram weight. And the moment arm here is this distance from the 50 grams all the way to the axis of rotation. And that distance is the 20 here plus the other 20 here. So the 20 plus 20 is 40 centimeters, which is 0.4 meters. And now we have an equation that we can use to solve for x. And here's the equation. 0 equals that minus that. Now to solve this equation, well, the first thing I see is that there's a 9.8 in every term, so that can cancel out. Although we did need to put it there to be really technically correct with our analysis here. So our simplified equation becomes this. Now I'm going to move both the negative terms to the left side of the equation, and they will become positive. And now it's just some simple math to solve for x. And there you have it. And I can also tell you there will be a problem on your test featuring Rocky the Raccoon, where you should take this exact approach.